Hello there. In this lecture, I'm going to discuss various methods of computing the deflection of beams under a variety of loading conditions, and we will see how we can apply that to the design of a stepped shaft. In general, there's a wide variety of methods for calculating beam deflections. And deflections include both displacement, vertical displacement up and down, and they also include a change in the slope of the beam itself, which both cases, the displacement up and down and the slope, are two parameters that are required in actual design. So what we will see is that there's basically 4 or 5 different methods, and as you can see on the slide next to me here, that the first method is called superposition, in which we use tables, and the tables are for very simple loading cases, and then we can make a complex loading case as a superposition of the results from each simple loading case. That is sometimes used by designers, but this is kind of a little bit old method. Before, people were able to do either precise hand calculations using a computer program like MATLAB or using numerical integration. So the next method that you will see is called the moment area method, and that is used mainly for indeterminate beams, and it's more of a graphical method. And then the third method is called the singularity functions, and the singularity function is a method to apply both concentrated loads and distributed loads on a beam, and then use mathematical integration of these functions to obtain the deflection and the slope. And it can be applied either to determinate or indeterminate beams as well. Next is the numerical integration, and that is just solving a differential equation of the fourth order, d4y by dx to the power 4 equals to the applied load q as a function of x, and then we would do numerical integration. This is not really what we would like to use, and most, if we're going to go into the numerical direction, then we would prefer to use the finite element method rather than pointwise integration of the deflection equation. So if you go down the list, there are 2 additional methods. One is called the Castagliano energy method, and that is very widely used, in which we use the elastic energy that is stored in the beam, and from the elastic energy, once we compute it, then we are able to take derivatives with respect to the force, applied force, that thus we can calculate the deflections. And then the last topic is the finite element software, and there are many commercial software that you will be using, and one of them is COMSOL and the other one is Abacus. However, I will give a special lecture on finite element calculations for the deflection, and this method you can actually program by yourself, and it will be very powerful and very useful for design applications. So I will start here talking about the beam deflection. We will not focus on superposition, although there's an example on superposition here in the book, but we will skip that method because, as I mentioned, we will have a couple of other possibilities that we will be using throughout the course. So let's now look at the method of the singularity functions. So here I'll start discussing singularity functions as a way to mathematically express the loads, and then from the loads, by successive integrations, we are able to find the shear, and then we are able to find the slope, and then we're able to find the deflection. So the singularity functions are, this is a useful notation that is used to represent concentrated loads, or concentrated moments, or loads that start and end at a particular point. So we have 4 of them here that we would like to understand. So if you look at the first one is actually a function that is composed of actually a concentrated moment, and the concentrated moment means that we have at A exactly, we have a force that goes up, and separated from it at a small distance is a force that goes down. So we have F up and F down, and the distance between them is very small. Let's call it epsilon. So F times epsilon is a concentrated moment, and the concentrated moment is at the point A. So this is concentrated at the point A. So in order for us to represent the location of this function and the doublet that we have, we can, if we know the value of the moment, we can use the function x minus a to the minus 2 in between the angular brackets. And when we say this, when you have this expression x minus a to the minus 2, the meaning of this expression is that it does exist only at x equals a, and it doesn't exist anywhere else. So the value of the function is 0 anywhere else, and at x equals a, it goes to plus or minus infinity, because you have like 2 delta functions in here. And if we don't have a coefficient multiplied by this function, then the integral is equal to unity. But if we have a moment, as I said, like m is known as f times epsilon, and we put m here, then m times x minus a to the minus 2 is basically the value of a concentrated moment at x equals a. The property of this function is that the integration over all space of the doublet is equal to the delta function. And the delta function is x minus a, also we're using angular brackets, raised to the minus 1. So this is a delta function. This is a doublet. So the integration of a doublet is equal to the delta function. Now I'm going to show the here the way that you can see here the expression that we wrote. Now if we do next integrate the doublet and integrate the doublet and get a delta function. The delta function is represented by this expression x minus a raised to the minus 1, and is concentrated at x equals a. And the meaning of this expression is that it doesn't exist anywhere else other than at x equals a. So the value is 0 everywhere. And at x equals a, the value is plus infinity. So it goes 0 plus infinity and then down back to 0. That's the delta function. And the use of the delta function is to represent a force, a concentrated force. For example, if I multiply this x minus a to the minus 1 with an f, that would be a concentrated force at x equals a. The important feature of the delta function is that its integration brings in the unit step function. So the next one in integration hierarchy, this is integration here, is the unit step. And the unit step function means that it's a switching function. It turns on and off if the value is at A or different from A. So if we look at this switching function, we will see that the value is 0 when x is less than A. So this is important to show that this is less than A. And the value is equal to 1 when x is greater than A. So these are the two possible values of the step function, meaning it goes 0 all the way when x is less than A, and then when x becomes A or greater, then the value of the function becomes 1. So if you multiply the unit step function by a delta function, so if we multiply f times x minus A to the power 0, this means that I have a concentrated force at x equals A, and then this force becomes constant all the way beyond x equals A. So this means that this can be useful for the representation of uniform distribution of forces. So uniform forces here. Finally, we have here the next in the hierarchy. If we do the integration of the unit step function, we get the ramp function. And the ramp function is represented as x minus A, curly angular brackets to raise to the power plus 1. And the value of the function is equal to 0 for x less than A, and is equal to x minus A for x greater than or equal to A. This means that it's linear, straight line, and the slope of the straight line is equal to 1, and it is turned on at this point x equals A. So we have now described those functions that you can see, and to summarize, if I have a concentrated moment, I represent it by a doublet. If I have a concentrated force, I represent it by a delta function. If I have a uniform distribution of forces, I represent it by a unit step function. And then finally, if I have a linear distribution of forces turned on at a certain point, then I represent it by a ramp function. And as you can see, that these are integration. One is an integration of the next one. One word that I would like to add here is that we use these functions in a way that we have to interpret the meaning of the mathematical equation. For example, if we say 3 times x minus 2 to the power minus 2, that means that I have a moment, the magnitude of the moment is 3, and it's only concentrated at the point x equals 2. So that's it. So the power minus 2 means moment, minus 1 means a concentrated force, minus 0 means a uniform, and then plus 1 means linear. And then the x minus whatever the number is, A for example, it means that it either doesn't exist except at A, or is turned on at A. That's the meaning of those. So let's just continue and then take an example to illustrate this singularity function method in here. So in the example that we have is we have a very simple example in which I have a beam, and the beam has an applied force F, and it's applied at position A from the left and B from the right, such that A plus B is equal to L. Then if I do statics, then I have two reactions, R1 and R2, and I know that R1 plus R2 is equal to the applied force. This is the vertical equilibrium. And then if I take moments about point A or point C, I can obtain the values of R1 and R2. Very simple. So in this case, we obtain from that R1 is equal to FB over L and R2 is equal to FA over L. And then the vertical shear at between A and B is R1, and between B and C is minus R2. So if I construct the shear diagram underneath here, then I would have this is the line, and then I would have a vertical value of R1 here, and then under the force F, then I will have a change, that the change in the shear is the same as the magnitude of F, and then I would have minus R2, and this is plus R1. So this is the shear force diagram. This is the actual for applied force diagram, and therefore for us to find the deflections, we can do the integrations of V to obtain theta, and then do another integration to obtain the displacement. So instead of doing that, as I mentioned before, we obtain the moment distribution between the 2 points A and B, and the moment between A and B is FBX over L, and between B and C is FAL times L minus X. So these are the two moments that we obtain in these regions. And we could do direct integration of we know that M over EI is equal to Y double prime, and then we integrate to obtain Y, and this integration gives us two functions, one function between A and B and one function between B and C. So this is kind of the combined graphical integration method. Let's see now how we're going to do that with the singularity function approach. So we want to do exactly the same procedure, which is repeating the integration method, but rather than just dividing it into pieces and doing it partly graphically and partly by integrating equations, I will just write an expression for Q using the singularity functions, and then I will just use the integration of each singularity function to obtain from Q I obtain V, from V I obtain theta, from theta I'll obtain the deflection. So watch this, how this will work. So let's see, we have here the way that we're going to write Q is I'm going to write Q as now the composition of three concentrated forces. One force R1, and it is concentrated at 0. So when it's concentrated at 0, we write x minus 0, and it is a delta function, so the power will be equal to minus 1. So, and the magnitude is R1. So you get R1 times x, and x is in between angular brackets. Same thing now we could apply to f, because f will be minus f, because going down is a negative function. And then on the right hand side of the beam there's a reaction R2, and is concentrated at x equals L, so we write it as R2 times x minus L raised to the power minus 1. Now the nice thing about singularity functions is that integration just all it does is raises the powers of here. So you go from Q to V, you raise the power from minus 1 to 0, and for all of them. And then you go from V to M, you raise the power of 0 to 1 for all of them. So at this point, we have an equation for the moment, and the equation for the moment is As you can see here, it's an equation that has basically three terms. One is related to the reaction on the left side, one term on the right side, and one term that is composed of the force going downward. So in order for us to proceed further with the integration, I need the values of R1 and R2. What is R1 and R2 that I can put into this expression? Because if I know the values of R1 and R2, then I should be able to find the moment, and then I'll be able to integrate it properly. Now I can do this two ways. One is to use statics, and in order for me to use the statics, I just write two equations and two unknowns. One is the force equilibrium equation, and the other one is moment equilibrium equation. I will obtain R1 and R2. Another way, which is exactly equivalent, is to set V equals M equals 0 for x slightly greater than L, which means that you equate this to 0, you equate this to 0. This is the force equilibrium. Sum of the forces equal to 0. This is the sum of the moments equal to 0. And when you put x slightly greater than L, then it means that you can evaluate R1 times L minus F times L minus A plus R2 times L minus L, which is 0, and equate that to 0. And note that when you have anything raised to the power 0 is equal to 1. That is exactly the same as saying that F is equal to R1 plus R2. And then the sum of the moments equal to 0. This is the moment of the reaction R1 when you put x equals L. And this is the reaction, this is the moment of the force F, and this is the moment of R2. And from these two, you can obtain the values of R1 and R2. And therefore, we have now an equation for the moment distribution that we could use to build up the slope and the deflection. So now you can guess what I'm going to do is that I reach that point that is comfortable for me, and that is to find the moment as a function of position. Once I find the moment as a function of position and it doesn't have any unknowns in this equation, all what I have to do now is integrate once and using the proper integration rules for the singularity functions, and integrate it twice, and then I'm done with the deflection. So let's do that to practice on the rules for integration of the singularity functions. So if I integrate anything that has power, as I mentioned before, anything that has power -1, you integrate it, you just increase the power. From 0 to 1, you increase the power. Once you reach power 1, then you're talking about normal integration rules, because you have a function that is just switched on at the angular brackets means the function is switched on at a particular location. That's all what it means. So if you have R1 times x to the power 1 and you integrate it once, you should get R1, which is FB over 2L, times x squared, because x squared over 2 is the result of the integration. And again, when you integrate this f times x minus a one time, you get f times x minus a to the power 2 over 2, and you have now the value of the integration. And finally, you integrate the third term, and don't forget to put the constant of integration C1 at the end. We then wait, so this is the slope, this is the equation for the slope. Essentially, theta is equal to that for the slope. Theta is equal to dy by dx, okay? So here you have this is theta times EI essentially. So we have to be a little bit careful in putting theta times E times I. So I'm going to write it a little bit clearly here. So if I have this is equal to E times I times theta as we will have defined it. Then another integration from dy by dx, I get y. Notice that second order becomes cubic over 6 because 2 times 3 is 6. And the same 6 here, same 6 here. And c1 integrate becomes x. And then we add a c2. Now the c1 and c2 we can obtain them using boundary conditions. And note that if we have the singularity function, if we have any x greater than 0, then you might as well just make x in between these angular brackets to be a normal polynomial. So everything in between brackets for x greater than 0 should be a normal polynomial. The other one would be equal to, would be left as a switching function, x minus a to the power 2 or power 3. And then we have now these two constants c1 and c2 that we need to determine from the boundary conditions. And the boundary conditions that we will have is that at y is equal to 0 at x equals 0, and also y is equal to 0 at x equals L. If we substitute x equals 0, then we find that c2 is equal to 0. And then we're left with only the value of c1 to be determined. That's the only term. c2 will be equal to 0 because everywhere else, when we substitute x equals 0, then we get a 0. Note in particular that this term here does not exist when x is equal to 0 because it's a switching cubic polynomial at x equals a or greater, so that it exists for x equals a or greater. So moving forward, then we can determine the constant c1, and finally now we have an expression for the deflection that is only one single expression, and note that it takes care of two regions because of the switching function here, x minus a cubic, and you can actually compare it to the previous work that was done here, that you have actually two different values of functions, one in between a and b, and the other one is between b and c. So the value of this method of determination is that it gives us one single expression for determination of the displacement at any point in the beam. So if we just want to summarize, if I'm doing a design, what is my objective? My objective is find the deflection equation and then to find the maximum value of the deflection, which could be obtained either by differentiation at the point of maximum or by knowing where to look for it from geometry. Another aspect is that we can compute the angle of deflection once we know y prime, because y prime is essentially equal to theta in radians. And that will finish the lecture, and in the next lecture I will be able to give another example, and then we apply it to the shaft design as we will see in the next lecture.